Hello everyone. In this video we will be discussing the generalization of our integral and single variable calculus to multiple integrals for functions here of two variables. So first let's remember the situation in Calc 1, right? So our definite integral, so we're just going to assume we have a nice continuous function so that this all works out. And our definite integral here gave us the signed area under our curve, right? So if this is our curve f, then we get the signed area from a to b. The issue, of course, is that we can't always use our fundamental theorem of calculus and find a nice antiderivative here. So let's recall what our actual definition of this definite integral is. Right, we have the limit of the Riemann sums where, we divide up our interval from a to b, as I did over here with our little blue dashes there, and then say we choose like our right endpoints, right? We get a whole bunch of rectangles and we are able to add up these areas and we get our approximation, right? And the issue, of course, again, is it's an approximation, and so we end up making them closer and closer together, have thinner and thinner slices, and we take the number of rectangles off to infinity to get an exact answer for our area, right? So now let's try to translate this and see what the analogous situation would be in a function of two variables. All right, so when we have two variables, right, our domain looks a lot different. We're not talking about an interval. So here we're going to be continuous on a domain R, which for us right now, we're going to talk about rectangular regions first, where things are a little bit easier, and then later we will talk about regions that are not rectangular. So, we have some rectangular region. This will be our x and our y axis, and this will be our z. So, let's say our domain looks something like this, right? We've got a little rectangle in the xy plane. And then let's have our f be, this bowl. So this would be something like x squared plus y squared, for instance. Okay, so then we no longer really have area under the curve, right? So instead we have this like bowl that gives us like a surface up above our region. And then when you talk about like what is under it, I mean, that's a three-dimensional thing, right? We're talking about volume here, right? So we've got like the volume underneath this guy, right? This is in 3 dimensions, so it's hard to see what I'm doing there, but like we have all this volume underneath our thing. And so the analog to area under the curve is going to be volume under a surface. And then how we compute this is still going to be a definite integral, but we're going to write it in a different manner. So what we wrote before as like the integral from a to b of f of x dx, we now would write the integral, but it's like a double integral here over the region R, since we don't necessarily have individual things assigned yet. So we'll just say over this whole region of f of xy, and then we usually say dA because we're talking about the area of a subregion, because what are we dividing this into? So if you look at your domain here, instead of having one interval that we subdivide, right, we have this whole rectangle that we subdivide. So we can subdivide it into a bunch of smaller subrectangles, right? And so when you talk about the area, I'm talking about the area of these little subrectangles here. So area of a subrectangle. And this is going to be the key ingredient for when we talk about Riemann sums and how to actually compute these things. Okay, so let's talk about that next. All right, so let's look at that same function and start looking at like what does a Riemann sum look like. So here I'm defining my rectangular region to be 0, 2 cross 0, 2. So we just go from 0 to 2 in our x and our y coordinate. And here I'm going to do 4 subrectangles first. And, usually we choose them to be of the same area, all congruent to one another to make life easy. And so in this case, right, we have 4 subrectangles, all area 1, because they're all just, width 1, height 1. And then what I need to do is I need to pick points in each one, right, to test. Because think back to what you did in Calc 1, right? You have some interval, and then you usually choose like your left endpoint, and then you get the height there, right? Well, we need to do the same thing. We need to test the height at the point, whichever one you choose. So here, let's do the lower left in each rectangle. So get this, 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 and this. So we'll do the lower left. And then what you're going to get is check the height. So check f of, well, this point is 0, 0, f of 1, 0 down on the bottom, f of 0, 1, and f of 1, 1. Then our Riemann sum here would be, well, we just take the height times the area for each one, and we sum them up, right? And then this is going to give us a volume because each rectangle is contributing both height and area, and when we multiply those, we get volume. And so here, we're going to get f of 0, 0 times, well, my area is 1, plus f of 1, 0 times 1, plus f of 0, 1 times 1, plus f of 1 times 1. And then you just figure out what all of these are, right? So this is 0. Here we get 1. We get 1. 1 squared plus 1 squared, we get 2. And so an approximation for our volume would be 4. And so what you really have here, right, are a whole bunch of rectangular prisms, right? We're approximating by rectangular prisms. And so that is kind of the analogy between this and single variable calculus, but we're up a dimension. So we took approximating by rectangles to approximating by rectangular prisms. So this is what a picture of the rectangular prisms would look like on the previous case, right? So our f of 0, 0, 1 had height 0, this had height 1, this had height 1, and then the one from 1, 1 up to 2, 2 there had height 2. And so you can see how if you have a bowl, right, it's going to look somewhat like this. Obviously, it's not a great approximation, but you can see how it's getting taller the further you go out from the origin there. So this is just an idea of what's going on. And so then if we were to continue the process, right, we would go up to, say, 16 subdivisions, and you would check out the area of each of these, right? And so these are all area 1/4 because they have width and height 1/2. And then you would check, whatever points you want. You could do all top right and, end up with something like this for the things that you plug in. And this is, in general, how you choose your Riemann sum. And so if you actually want to define the integral here, the integral over the region of x, y, dA is the limit of course, the Riemann sums again. And so how do I define my Riemann sum this time? Well, I plug in some point, right? So xi, yi, say, in my ith subrectangle. You can just count them up. Say this is 1, 2, 3, 4, 5, 6, 7, 8. Who cares, right? You can number them however you want. Point is you pick a point in all of them, 1 point, and then check the height there. And then you've got your delta, and it's not x, right? It's like the delta AI, where this is the area of the ith subrectangle. And the way that we choose them so that they're all congruent to one another is that this is a constant, right? And so this is the idea, and this is how we officially define this. And so in class, we will talk more about how to actually use the integration techniques that we developed in Calc 1 to actually compute these, right? Because ideally, we're not doing a bunch of Riemann sums every time. We would like to use our knowledge of antiderivatives, and we'll see that we can still do that. Okay, and so for your only exercise here, I want you to calculate the Riemann sum for x plus y instead of x squared plus y squared on a little bigger rectangle, so the one from 0 to 4 in each coordinate, with 16 subrectangles, and I want you to do, we'll say, the top left corner of each rectangle. for your test point. Okay? Alrighty, well, thank you for watching.